Hello everyone, welcome to this lecture. So, the plan for this lecture is as follows. In this lecture, we will focus on perfectly secure multi-party computation involving 3 parties, and among those 3 parties there could be one semi-honest corruption. We will first see the motivation for studying this special case of multi-party computation, namely the case of 3 party computation, which we also call as 3PC, and then we will see a concrete protocol. So, let us first understand the problem setting. We have a set of 3 mutually distrusting parties P1, P2, P3. Of course, we are in the pairwise private channel model, where we assume that there is a private channel between every pair of parties here, and each party has some private input. So, the inputs are x1, x2, x3. Okay. They could be from a ring or a free field. There is no restriction on the algebraic structure, and there is a publicly known function f, and the goal is to securely compute the function f. Okay. And corruption scenario here is that we assume that any one party out of these 3 parties can be passively corrupted by an unbounded powerful adversary. That means, after the protocol gets over, any one of these 3 parties might try to analyze the protocol transcript and try to infer anything additional beyond its own input and the function output. Okay. And we want to prevent any kind of leakage from happening through the protocol. Okay. So, the goal is to design a protocol which allows the parties to compute the function with perfect secrecy and correctness. Okay. Perfect secrecy means that the view of the semi-honest corrupt party should be independent of the inputs of the honest parties. That means, it can be simulated by a simulator, and by correctness we mean there is the output y, which is finally obtained by the parties, is the correct output. So, the question is why we want to focus on this specific case of 3PC. Okay. Because till now we are talking about we were talking about n party computation. Out of them, T could be corrupt, or we could have non-threshold adversary, but then suddenly we are now talking about a special case of multi-party computation where n is equal to 3 and T equal to 1. And there are several reasons for doing this, for studying this special case of 3PC. The first reason is that there are customized solutions which are tailor made specifically to deal with the setting of 3 party and tolerating 1 corruption. That means, these techniques will not be applicable for general n party computation and tolerating T corruptions. Not applicable in the sense you do not get the same efficiency which you would have obtained by applying those techniques to the special case of 3 party computations tolerating T equal to 1 corruptions. Okay. And those solutions, those customized solutions, as they are tailor made for 3PC, they gives you practically more efficient MPC protocols compared to what you could have derived by plugging in n equal to 3 and T equal to 1 in any generic MPC protocol, right. So, remember we have generic perfectly secure MPC protocols tolerating T less than n by 2 corruptions. Okay. So, for instance, we had seen the protocol based on Gennaro-Rabin degree reduction method. We also have the protocol by Damgard-Nilsson and so on. So, those protocols are for any number of parties and tolerating any number of corruptions, any T number of corruptions where T is less than n over 2. So, now if I substitute n equal to 3 and T equal to 1 in those protocols, I will have a solution for the 3PC, right. I will have a perfectly secure MPC protocol among 3 parties tolerating 1 corruption, but those solutions will be inefficient. They will require more communication, more number of rounds compared to the customized solution, the tailor made solutions that we have for the special case of 3PC. Moreover, Another motivation for studying this special case of 3PC is that in the protocols we do not require any stringent requirements from the underlying algebraic structure over which the computations are performed. So, for instance, both these protocols Gennaro-Rabin-Rabin, Damgard-Nilsson, they require a finite field. Okay. They require the function to be a function over a finite field, and that finite field should have cardinality greater than n, the number of parties. Whereas, as we will see later, these 3PC protocols they can be designed, the computations in these 3PC protocols, they can be performed both over the ring as well as over the field. There are no stringent requirements that you need to necessarily have the function over the field. In fact, we can design, we will be seeing 3PC protocols where the computations can be performed over a Boolean ring itself. Okay. So, you do not require a field whose cardinality is greater than the number of parties. So, that is another motivation. And the third motivation is that the special case of 3PC can be used for MPC among a large population, right. So, you might be wondering that this 3PC solution, what it cannot be used in a scenario where there are more than 3 number of parties to actually who are interested to perform computation on their private data, but that need not be the case. What we can do is we can outsource MPC for those large population, and that outsourcing can be done to these 3 servers. So, imagine you have million number of parties, an enormous large number of parties spread geographically, and they are not interested to run the generic MPC protocols, because running the generic MPC protocol over such a huge population might be inefficient. Instead, what those parties can do is they can hire these 3 servers, okay, and they can make their inputs available in secret shared fashion or whatever secure way they want to among these 3 servers, and then let these 3 servers perform the computation for all those parties, compute the function output and give back the function output to the parties. And the guarantee that we obtain here is that as long as only one out of these 3 servers, the hired servers, is semi honestly corrupted, the privacy and the correctness of the computation is guaranteed, right. So, it is not the case that by deriving techniques tailor made only for 3PC, we cannot perform NPC computation, secure NPC computation, right. We can actually perform secure MPC involving multiple parties by outsourcing the computation of those n parties to these 3 servers whose service can be hired. Okay. And indeed, there are several commercial, not commercial, several practical deployments of several 3PC protocols, and very nice results have been obtained. So, now we have several 3-party protocols which can perform very fast computation in a private fashion. Okay. Right. So, there are several motivations we have seen already. So, now we will see the concrete protocol, and again the protocol will be based on that blueprint of shared circuit evaluation, where it will be ensured that all the values in the computation remain secret shared among the parties in one with threshold being t equal to 1, okay, because there could be up to 1 corruption. So, the threshold will be t equal to 1. So, it will be ensured that all the values in the computation will be secret shared, and all the gates will be evaluated in a secret shared fashion, and then finally, once the function output is ready in secret shared fashion, the parties go and reconstruct the function output. But now the difference here will be we will not be using the Samir secret sharing protocol, because we now want more efficient protocols, because if we finally resort to Samir secret sharing protocol, then it is basically resorting to the generic MPC protocol. That is not what we want to do here. We want to design special secret sharing protocols, special way of performing multiplication, addition, reconstruction, and all those techniques will be tailor made for the case of 3 parties. Okay. So, the secret sharing that we will be using in this MPC protocol, in the 3PC protocol, is based on replicated secret sharing. So, let us first try to understand what is this replicated secret sharing, which I will also call as RSS. So, imagine you are given a ring R, okay, and there is no restriction on the cardinality of the ring. It could be as simple as the Boolean ring consisting of just the values 0 and 1, where the plus operation is actually the XOR operation and the dot operation is the AND operation, but in general it could be any ring. Okay. So, imagine there is a value S in the ring. We will say that a value is secret shared as per replicated secret sharing or RSS shared if there exist 3 values from the ring S1, S2, S3 such that the summation of S1, S2, S3 is equal to the secret S, okay, where the summation means the plus operation of the ring, and each party Pi holds the piece Si and Si plus 1, where if I is equal to 3, then I plus 1 means 1, because 3 plus 1 will be 4, but there is no fourth party or fourth piece. So, basically we do the wrap around, and then basically by I plus 1 I mean the first I plus 1 will denote the value 1. Okay. So, pictorially you can imagine that P1 will have the pieces S1, S2, P2 will have the pieces S2, S3, and P3 will have the pieces P3, S3, S1. Okay. And it is easy to see that this 3 party replicated secret sharing satisfies the linearity property. What does linearity mean? That means that any linear function of secret shared inputs can be computed locally. That means, if there is a linear function whose inputs are available in a secret shared fashion among these 3 parties as per this sharing semantic, then the parties can apply the same linear function. It can compute the linear function on the secret shared value itself. That means, by applying the linear function on their respective shares of the inputs, they can obtain their respective shares of the output, where the shares actually constitute a replicated secret sharing of the function output. So, imagine you have 2 values S and S prime secret shared as per replicated secret sharing, namely you have 3 pieces S1, S2, S3 summing up to S, and you have 3 pieces S1 prime, S2 prime, S3 prime summing up to S prime. Then each party can do the following: it can P1 can add up component wise its pieces of S and S prime. Okay, so, let us take a more generic linear function. Addition also is a linear function, but imagine that the parties want to compute a function which is C times S plus D times S prime. That is a function which parties want to compute, where C, D are public constants from R. Okay. So, that is a requirement, but S and S prime should not be revealed in the process. If that is the case, then what the parties can do is the following: the parties compute a linear combination of their respective shares of S and S prime as per the linear combiners C and D. So, party 1, it computes this linear combination. So, it will obtain a pair of values, P2 will obtain a pair of values, and independently P3 will obtain a pair of values. And now, if you see that this 3 pieces, the 3 pieces in the sense the pair, the values C times S1 plus D times S1 prime, and then C times S2 plus D times S2 prime, and then C times S3 plus D times S3 prime. If you sum all of them together, you get the value C times S plus S prime, C times S plus D times S prime. and as per the semantics of replicated secret sharing, the value C times S plus D times S prime is now available in a secret shared fashion. So, that means any linear function can be computed locally, and in this replicated secret sharing, the share for each party will be a pair of elements, it is not one element, right. So, share of each party, share of P I is equal to the values S I and S I plus 1. Okay. So, definitely in terms of share size, this is bad, because if we consider the summit secret sharing, there the size of each share is the same as the size of the secret. That means, if secret is a single field element, then the ith share also will be a field element. But here if the secret is a field element, of course, all the operations I am doing here over the ring, but the same operations can be performed over a field as well. So, imagine if my secret would have been from a field, then the share size for each party will be twice the number of elements, or twice the number of bits basically that you require to represent one field element. So, the share size is twice compared to the secret size. So, that is bad, but later we will see that even though the share size is more than the secret size for each party, it if we perform secret shared circuit evaluation as per the semantics of replicated secret sharing, then we get more efficiency, right. So, that is a sharing semantic of replicated secret sharing. Now, we have to see the protocols for sharing a value as per replicated secret sharing, and now if a value is secret shared as per replicated secret sharing, how you can reconstruct it and so on. So, imagine S is a value available with a dealer, and it needs to be secret shared by the dealer. So, what the dealer is going to do as part of the secret sharing protocol, it will randomly pick 3 values from the ring. So, I am assuming that a secret is from the ring and all the computations are also performed over the ring. So, it will randomly pick 3 values from the ring such that the summation of those 3 values is equal to the secret S. How it can do this? So, it can randomly pick S1 and S2, and it can then set S3 to be the difference of S and S1 plus S2. And then the share for the ith party will be the pair of values Si and Si plus 1. So, pictorially, if P1 is the dealer, then it will do the following. If it wants to secret share a value S, then it will pick 3 random pieces S1, S2, S3, which sums up to S. His own share for the secret S will be S1, S2. So, it need not have to communicate S1, S2 to it himself, but he has to communicate the shares to the other 2 parties. So, he communicates those required shares over the private channel. Similarly, if P2 would have the value S prime which it needs to secret share, it will compute the values S1 prime, S2 prime, S3 prime summing up to S prime, and then distribute the respective shares and so on. Now, it is easy to see that in this protocol, if the dealer is honest, then the privacy of S is maintained, namely among these 3 parties, if one of the parties is corrupt, and of course, I am considering the case when that corrupt party is not the dealer, because if the dealer himself is corrupt, then it knows the full secret, because it itself has generated the shares. We have to argue about the privacy when the dealer is honest. So, my claim is that if the dealer is honest, then an adversary who can corrupt any one of the remaining 2 parties does not learn any information about the secret, namely its view will be independent of the secret, namely whatever share it receives, it will be independent of the secret. And that follows that follows from the properties of additive secret sharing, which we had already seen earlier. So, imagine if P2 is bad. So, what exactly will be her view? The view will be the probability distribution on the pieces S3 and S1. Why probability distribution? Because these values S3 and S1 they are randomly picked. they are not fixed values. So, that is why her view will be having a probability distribution over S3 and S1, but this S3 and S1 could be equilikely the shares for the secret S, or equilikely they could be the shares for S prime as well, because it is quite possible that there is a value S2 which along with this S1 and S3 will give S as the secret, and it is equiprobably that it is equiprobably the case that there is another value say S2 prime which along with the same S1 and S3 would result in the secret S prime. But since the piece S2 is randomly chosen in the secret sharing algorithm in this replicated secret sharing, this corrupt party cannot infer whether she is seeing the shares for the secret S or for the secret S prime, right. That means, whatever communication happens in this protocol and whatever is the view generated for the adversary, that can be easily simulated. That means, this adversary's view can be simulated, and the distribution of that simulated view will have the same will be the same as the view generated in the actual secret sharing protocol. The protocol will require one round of communication, because it is only the dealer who has to talk and distribute the shares, and it can distribute the shares independently. So, it is not the case that it has to first communicate the shares S2, S3 and then it has to communicate the shares S3, S1, no, because it has independent channels with independent parties. So, it can use those channels at the same time, and the total communication here is 4 ring elements. That means, if dealer has 1 ring element to secret share, then it has to totally communicate 4 ring elements. Okay. So, now what we will do here is the following. We will see that can we reduce the cost of this secret sharing protocol in terms of communication. Of course, interaction has to be there. Dealer has to distribute the shares, because if the dealer does not distribute the shares, then how can secret be made available in a shared fashion. So, definitely we cannot compromise on the number of rounds here, because that is the optimal thing here, 1 round. We have a possibility of further improving the communication complexity, assuming that there is some pre-processing phase which will be done before the actual sharing happens. Okay. And remember, we had already seen the motivation for pre-processing based MPC. The idea is that if there is a scope of shifting or preponing all the complex operations in a phase which is independent of the circuit, and then using the data generated in the pre-processing phase, if we can optimize, if we can make the actual shared circuit evaluation faster, then there is a big advantage, and we are trying to follow the same principle here as well. We are looking, we are trying to see whether there is a possibility that the parties generate some raw data from pre-processing information in a function independent, circuit independent, input independent pre-processing phase, and with the help of that raw data, the actual communication complexity of this sharing protocol gets reduced. So, the answer is yes. Imagine in the pre-processing phase, the parties generate random values alpha 1, alpha 2, alpha 3 in a secret shared fashion, such that those alpha values are random, but they sum up to 0. So, you might be wondering that if they sum up to 0, then how can you say alpha 1, alpha 2, alpha 3 are random? Well, it is quite possible that alpha 1 and alpha 2 are randomly chosen, and then I set alpha 3 to be the difference of or minus of alpha 1 plus alpha 2. So, even that will be a random vector of 3 values summing up to the value 0, right. So, imagine in the pre-processing phase the parties interact, there is a mechanism by which they interact and generate this setup. How this setup will be generated, that will be the focus of our next lecture, but imagine for the moment that whenever there is a requirement of generating such a system here, namely a system of 3 random values summing up to 0, and P1 having the first component, P2 having the second component, P3 having the third component, that is always possible. And remember here, this is not RSS sharing of 0? No, because the parties know that a value 0 has been shared. The secret 0, there is nothing called secret here which has been shared. P1, P2, P3 will know that okay, it is a 0 value which has been shared. P1 will have only one of the shares, namely alpha 1, P2 will have one of the shares, namely alpha 2, and P3 will have the third share, namely alpha 3. And you require here at least two parties to collaborate to learn the full alpha vector, right. So, if say P1 and P2 collaborate, then they can find out what is alpha 3, because they know that alpha 3 when summed up with alpha 1 and alpha 2 should have produced 0, right. But if only one party tries to find out what are the remaining two pieces, it cannot find out. That means, if I just consider P3, P3 will have alpha 3, but it will not be knowing what is the alpha 2 and it will not be knowing what is the alpha 1, okay. And it knows it is sum up to 0. So, it could be any alpha 2 and any alpha 1s with along with alpha 3 could sum up to 0, not any. Once it fixes alpha 2, corresponding to that alpha 2 there will be a corresponding alpha 1 which along with the fixed alpha 2 and alpha 3 which is available with P3 will sum up to 0, right. So, that is a setup parties would have generated. Assume for the moment that such pre-processing is possible. Now, assuming such pre-processing is possible and now say P1 is the dealer who wants to secret share a value S, then it can do it as follows. Similar actions can be done if P2 would have been the dealer or P3 would have been the dealer. So, it is not necessary that for this sharing protocol it is only P1 who is the dealer. I am, for the purpose of demonstration, I am just taking the case where only P1 is the dealer, but similar actions can be performed if P2 is the dealer or P3 is the dealer. Whenever a value has to be shared by the dealer, we will assume that in the pre-processing phase a random vector of alpha 1, alpha 2, alpha 3 have been generated with summing up to 0. Now, the idea behind this efficient sharing phase protocol is the following. We know that the summation of alpha 1 and alpha 2 and alpha 3 is 0. Now, what can we say about the summation of S plus alpha 1 and alpha 2 and alpha 3? Well, we can say that the summation of these values is actually S, and our goal is to generate a secret sharing of S as per replicated secret sharing. So, based on this observation, what we can do here is the following. Party 1, who is the dealer actually, will compute this value S1, and this value S1 is said to be the summation of S and alpha 1. So, you can imagine it as an OTP encryption of the secret S, which will be now given to P3. Why given to P3? Because remember, as per the sharing semantics of RSS, the secret which has to be shared has to be divided into 3 pieces summing up to the secret, and each party should have 2 of those 3 pieces. So, basically we know here from the mathematics, from the algebra here, that S is actually the summation of these 3 pieces. So, I can set the term here in the parenthesis as S1, I can set alpha 2 to be S2, I can set alpha 3 to be S3. So, now we have 3 pieces whose sum is actually S, and we need to ensure that each party should have 2 of these 3 pieces as per the semantics of replicated secret sharing. So, for instance, P3 should have the third piece as well as the first piece. Third piece is already available with him, alpha 3, from the pre-processing phase itself. The first piece needs to be communicated to him, and the dealer can communicate that piece to him. In the same way, the second party, he already have the second piece here, namely alpha 2, okay, but he also needs the third piece as per the sharing semantic of replicated secret sharing, and now P3 can provide a third piece to him, the third piece namely alpha 3. And in the same way, P1 should have both the first piece and the second piece. First piece it already has, second piece party P2 can provide, and this will complete the replicated secret sharing of the value S, it still requires one round, but now the communication for the actual sharing is 3 ring elements compared to 4 ring elements, right. So, earlier if there was no pre-processing data available and at the run time when the value S is available for the dealer to be shared, if it directly tries to secret share it as per the replicated secret sharing, it would have required 4 ring elements. But now assuming that some raw data is available from the pre-processing phase, the cost of the actual sharing be reduced from 4 to 3 ring elements. Now, you might be wondering that how much saving is from, whether it is a big saving, reducing the communication from 4 ring elements to 3 ring elements. Imagine there are millions of values which the dealer D or the party P1 would have wanted to secret share during the MPC protocol, and indeed even for a simple function, even for very simple functions, we encounter cases where each party has to secret share as a dealer several values, millions of values. So, if there are millions of values which needs to be secret shared, then reducing the cost, communication cost from 4 to 3 ring elements is indeed a big saving, because we are now saving 1,000,000 ring elements in terms of communication at the actual time of sharing the protocol. Of course, you have to pay the price of the pre-processing phase, but remember we are assuming that the pre-processing could have been done in advance when actual circuit, actual function is not yet ready for computation, for evaluation. Okay. Now, why this modified secret sharing protocol is still private like the earlier protocol? So, again we are taking the case when P1 is the dealer here. So, if the dealer is honest, and we have to argue that if P2 or P3 is corrupt, then its view is independent of the actual secret. So, imagine if P2 is corrupt. If P2 is corrupt, then what will be its view? Its view will be alpha 2, because that is S2, and alpha 3, which is S3. But alpha 2 and alpha 3, they are completely independent of the value S, which is actually shared, because this alpha 2 and alpha 3 would have been generated in the pre-processing phase, and it has absolutely no relationship with the secret S. So, that is why a corrupt P2 does not learn any information, whereas if we consider the case where P3 is corrupt, its view will be S3, which is alpha 3, and S1, which actually has something to do with the secret, but S1 is actually S plus S alpha 1, and alpha 1 is a random element. Alpha 1 is actually acting as here a one time pad key, and S1 is acting as the one time pad encryption. Now, since the pad alpha 1 is not known, why the pad alpha 1 is not known to this corrupt P3, potentially corrupt P3? It knows alpha 3 fine, but it does not know alpha 2 and alpha 1, even though it knows that they sum up to 0. So, it could be any alpha 1, and corresponding to that alpha 1 there is an alpha 2 which would have summed up along with S alpha 3 to be 0. And now that alpha 1 is acting as the pad and is getting S plus alpha 1. So, that will not reveal any information. Now, remember next time again the dealer wants to secret share a value, say P1 again wants to share a value, say S prime, we need a fresh pre-processing data to be available. Okay. So, we cannot use the same alpha 1, alpha 2, alpha 3 and let the dealer use the same alpha 1, alpha 2, alpha 3 setup for sharing all the values which it wants to secret share. For every value S which it wants to secret share, there has to be an independent, there has to be a fresh alpha 1, alpha 2, alpha 3 which has to be made available from the pre-processing phase. So, you can imagine that if in the sharing phase there are billions of values which needs to be secret shared, then in the pre-processing phase we need this setup of alpha 1, alpha 2, alpha 3 billion number of times to be generated. Okay. Now, let us see the reconstruction protocol. Assume that we have a value S which has been shared in the replicated secret shared fashion, and now we want to publicly reconstruct it. Okay. Now, to publicly reconstruct it, we need to ensure that all the 3 pieces are available with every party. Right now, every party will just have 2 pieces. So, the way we ensure that every party has all the 3 parties have 3 pieces is the following. We ask P1, we ask Pi to send Si plus 1 to the next party in the sense along the circle. So, you imagine a circular arrangement here where P1 is followed by P3, P3 is followed by P2, P2 is followed by P1. Okay. And as of course, you can change the circular order as well, that is not important. Once we fix the circular order, then as we have to follow the protocol as per that circular order itself. So, we can ask P1 in the protocol to send the piece S2 to P3, that will ensure that P3 has now all the 3 pieces. We ask P3 to send S1 okay, to P2 and actually it should be Pi to Pi minus 1 okay, because 3 is sending the piece number Si minus 1. Of course, there can be other ways of also, because if I change the circular order, then that would have followed what I have written down earlier, but for the demonstration I am assuming this order. So, Pi sends the piece Si minus 1 to the I minus 1th party, where if I take P3 to be Pi, then it is sending the piece S1. So, again this is not a Pi minus 1. Okay, so, let us not go into the formal thing here. We can come up with the exact formal thing here, but you can imagine that the parties are arranged here in the circular order and we follow the circular notation in terms of communicating the messages that P1 should send P2 to S3, P3 should send S1 to P2 and P2 should send S3 to P1, and that will ensure that all the 3 parties have all the 3 pieces and then they can reconstruct back the secret. So, now the nice thing about this reconstruction is that each party now needs to talk to only one party, right. It is not the case that every party has to send its share to every other party for the full public reconstruction. Each party just need to talk to one of its neighbor, and we can fix that one neighbor as per a circular order in the protocol. So, P1 we can fix that it talks only to P3, P3 talks only to P2, P2 talks only with P1, and this can happen in parallel. So, that is why it takes one round of communication and total 3 ring elements are communicated. And this nice feature that each party talks only to one party was also followed in the efficient secret sharing protocol that we had discussed earlier. In that efficient secret sharing protocol also, the dealer who was P1 was talking only to P3, P3 was talking only to P2 and P2 talks only to P1, right. It is not the case that everyone is talking with everyone or interacting with everyone. So, that makes this sharing protocol very nice, and we will see that we will maintain this property, this nice property of circular communication, where each party just sends or communicate to only one of its neighbors during the circuit evaluation protocol as well. Okay. So, now we had seen the secret sharing protocol, we had seen the reconstruction protocol, we know that this replicated secret sharing satisfies the linearity property. Now, what is left is to see whether we can evaluate the multiplication gates also in a secret shared fashion, assuming that the gate inputs are secret shared as per replicated secret sharing. So, consider a scenario where you have a multiplication gate in the circuit and the inputs of the gates are x and y, okay, and this could be any intermediate gate in the circuit. So, we are considering the setting when x and y are secret shared as per the replicated secret sharing, and now we want to ensure that the output z, which is x dot y, should also be somehow made available to the parties in a replicated secret shared fashion. And we will be interested to see whether this can be done non interactively, because we will prefer a method where all the gates can be evaluated in a shared fashion, and that too non-interactively, because if that is possible, that means that once all the function inputs are secret shared, then parties do not need to interact. They can just keep on evaluating their local copies of the circuit gate by gate by gate and go all the way to the output gate and then reconstruct a shared output. But it turns out that for multiplication gate it is not possible here to do it non-interactively. So, the goal of the parties is to compute replicated secret sharing of x times y, and x times y, if I consider, then basically that will be the product of x 1 plus x 2 plus x 3 and y 1 plus y 2 plus y 3, and then this can be written down as summation of 9 terms here, 9 summents here. Okay. So, sorry for this typo, this should be x 3, yeah. So, there are 9 summents here starting from x 1 y 1 going all the way to x 3 y 3. Now, we have to see whether there is a mechanism by which we can finally write down x times y as the summation of 3 pieces, and each of these 3 parties having 2 of those 3 pieces, because that is the sharing semantic of replicated secret sharing. Now, with that goal in our mind, let us propose the following. Let each pi computes this term zi. So, what does that mean? That means the following. So, P 1 it can compute x 1 times y 1, it can compute x 1 times y 2, it can compute x 1 y 1 times x 2. Of course, it can also compute x 2 times y 2, but we do not want to have one party computing more summents compared to other parties. Remember, we have 9 summents here and we want to distribute 3 summents to each of the parties. Okay, so 3 summents should be one of the parties, another 3 summents with another party, and so on. So, P 1 can take care of these 3 summents, he can sum them locally and obtain Z 1. P 2 can compute this summand and P 3 can compute this summand. So, it is easy to see that indeed the summation of Z 1, Z 2 and Z 3, that is equal to x times y because of the arithmetic. And now you might be tempting to do the following to ensure that the value x times y is made available in a replicated secret shared fashion, because remember we will be finally evaluating the entire circuit where the values will be secret shared as per the semantics of replicated secret sharing. So, if you now want to ensure that x times y is available in a replicated secret shared fashion, you might be tempting to do the following: ask P 1 to send Z 1 to P 3, that will ensure that P 3 has both Z 3 and Z 1, and in the same way ask P 3 to send Z 3 to P 2, that will ensure that P 2 has both Z 2 and Z 3, and so on. Now, the question is, will this protocol lead to a security breach? Remember, our goal is to ensure that when we are evaluating the multiplication gates, nothing about the inputs x and y should be revealed. So, before the multiplication gate evaluation started, what information about x and y was available with the adversary? So, for simplicity, assume that P 2 is the corrupt person, adversary. So, before the multiplication gate started, P 2 has no information about x 1, it has no information about y 1. Both of these two pieces are random from its viewpoint. But now, if I ask P 3 that you give Z 3 to P 2, so Z 3 is this value. Now, out of this value, P 2 already have x 3 y 3. So, it can subtract it from Z 3 and hence that will reveal this value x 3 times y 1 and x 1 plus x 1 times y 3. Now, you might be wondering that okay, this does not reveal the full value of y 1 or x 1, but what we can now say is that the view of the corrupt party, the party number 2, is no longer independent of x and y, because now it is learning an additional information for x1 and y1, which was not available earlier. Specifically, consider the case where say x3 is equal to 0, right. It could be possible that x3 is equal to 0. If x3 would have been 0, then this value is actually same as x1 times y3. So, basically adversary ends up learning x1 times y3, and since it already has y3, if y3 is not 0, suppose that means y was shared in such a way that y3 was not 0, but x was shared in such a way that x3 is 0, then by multiplying this value with y3 inverse, the corrupt P2 ends up learning x1. Now, if it is x1, then along with x2 and x3 it reveals the full x to the corrupt P2. That means, this protocol definitely is not secure, even though asking the parties to compute z1, z2, z3 produces 3 pieces whose sum is equal to xy, but as soon as we ask the parties that okay, you interact these 3 pieces with each other to ensure that the final thing is available in a replicated secret shared fashion, the security is breached. And the problem here is something very similar to what we faced during the degree reduction problem. There also we saw that if x was secret shared through a t degree polynomial, y was secret shared through a t degree polynomial, and if the parties just locally multiply their respective shares of x and y, not only it leads to the blow up in the degree, but it also causes security breach, because the resultant x times y is no longer shared through a random 2t degree polynomial, and the same issue is coming here. So, now what we have to do is but this protocol is very nice, because it has this property that each party just talks with only one of the neighbors. And remember, our whole motivation is to get a efficient 3PC protocol, where we would like that each party talks only once for every multiplication gate, and that too only with one of the neighbors. Okay. So, we would like to retain this blueprint, but to prevent this security breach, what we have to do is we have to ensure a mechanism where party pi should randomize the piece zi before sending it to the neighbor. Now, how exactly that randomization will happen, that will be the focus of our next lecture. So, the 3PC protocol based on replicated secret sharing that I discussed today in today's lecture is based on this paper published in 2016. Thank you.